Welcome back. In this module, we'll be delving into the world of soil chemistry. Here is an outline of what we'll be covering in this module. First off, we'll begin with soil pH, and then move on to a discussion of what are essential plant nutrients, and then finally move into a deeper understanding of nitrogen in our landscape. To begin, we will talk about soil pH. Soil pH is often called the master variable. This is due to the fact that soil pH dictates what chemical form essential plant nutrients will take, and then it will determine if these nutrients are plant available. We'll talk more about this in the next slide, but let's first define what is pH. pH is a measure of the concentration of hydrogen atoms in solution. pH is defined as a negative log base 10 concentration of hydrogen atoms. Let's break this down a bit more so we can get a better understanding of what pH is telling us. Since we're using a negative concentration, this means the lower the pH, the higher the concentration of hydrogen is. Since it is a log base 10 scale, that means a change in 1 unit on the scale is 10 times more or less concentrated from the previous number. To tie it all together, a soil of a pH of 6 has 10 times more hydrogen atoms compared to a soil of a pH of 7. Here is a classic figure you should commit to memory. How we interpret it is along the x-axis we have soil pH, moving from strongly acidic on the left to strongly alkaline on the right. Each one of the bars along the y-axis represents an essential plant nutrient. The thicker the bar, the more plant available that nutrient is. As you can see, many bars are the thickest between a pH of 6.5 and 7.2. That is an ideal soil pH. The major factor in determining soil pH is the amount of precipitation a location receives. The higher the amount of precipitation, the lower the soil pH will be. Here is a map of precipitation patterns around the US. And if we took a map of soil pH and overlaid it with this precipitation map, they would match up almost exactly. The areas with green and blue have soils with a low pH. The brown and tan areas have soil with a neutral pH. And in the areas that are olive, yellow, and orange, those soils typically have a high pH. So what does this all mean for us as gardeners? Well, it means soil pH will dictate what we can and cannot grow. Some plants have evolved to really enjoy low pH soils. These include, but are not limited to, blueberries, azaleas, and rhododendrons. For those three plants, it's very hard to grow them in neutral or high pH soils. However, many plants enjoy that soil pH closer to neutral. And so if you are dealing with a soil that is very acidic, what you can do is to apply lime. This will actually raise the pH of the soil closer to neutral. These applications have to be done yearly, and application rates are based on what type of lime you are applying. Here in Colorado, this situation is very rare. If you are fortunate enough for your soil to be naturally in that range of 6.5 to 7, then there's no need to worry about your soil pH. However, here in Colorado, only some of our soils meet that criteria. Because of both of our low precipitation rates and parent material, many of the soils found here in Colorado are alkaline, meaning they have a pH that is greater than 7. It is not uncommon for soils here in Colorado to have pHs above 7.5. This can lead to nutrient deficiencies in our landscape plants because remember, at high pH, these nutrients become chemically unavailable to plants. Iron is one common deficiency with soils that have a high pH. This deficiency leads to what is known as iron chlorosis. We will see some examples of this on the next slide. The other major pH issue with Colorado soils occur if the soil has a high concentration of calcium carbonates. This is also known as free lime. Soil with a high concentration of free lime will resist almost all efforts to lower the pH closer to neutral. This is because the calcium carbonates act as a buffer to the acids and quickly neutralizes them. Here are two pictures of trees suffering from an iron deficiency and showing iron chlorosis. Chlorosis means yellowing, and for iron chlorosis, you notice that the veins remain green while the rest of the leaf yellows. If you have a soil with high pH, there are a few strategies you can employ. If you have a soil with a high pH and high free lime, it is best only to plant species that can tolerate the high pH. If your soil has a high pH and no free lime, then you can apply sulfur to help lower the pH. Sulfur applications take time to change the soil pH, so it is best to retest your soil after 3 or 4 months. Another important thing to consider is your irrigation water. If you are irrigating with water that has a high pH and/or mineral content, this can compound nutrient availability issues. If that is the case, it may be worth looking into treating your irrigation water before application.
This wraps up our conversation on soil pH. We will now talk about essential plant nutrients. Here is a handy mnemonic device to help you remember what elements are essential to most life here on planet Earth, plants included. The mnemonic device is Chopkin's Cafe MG. This stands for the elemental symbols of carbon, hydrogen, oxygen, phosphorus, potassium, nitrogen, sulfur, calcium, iron, and magnesium. This is a big list, but plants also need manganese, boron, molybdenum, and chlorine in small amounts in order to grow. Those are what are known as micronutrients. The first set of nutrients we'll talk about are the macronutrients, nitrogen, phosphorus, and potassium. Plants need these nutrients in a relatively high amount compared to other nutrients. That is why they're given the term macro, which means large scale. The interesting thing about these nutrients is that they are mobile within the plants. That means plants can take these nutrients and use them for multiple essential biological processes, but then break them back down and move them through their vascular system and into parts of their tissues as needed. How this typically plays out is that if a plant is experiencing a deficiency of any of these mobile nutrients, it will take the nutrients out of the old tissue and pump it into the new growth. Because of this, you will see deficiency syndromes of mobile nutrients first in the older leaves, which are typically on the lower parts of the plant. The next class of nutrients are the secondary macronutrients. These are sulfur, calcium, and magnesium. Plants need these nutrients in lower quantities compared to nitrogen, phosphorus, and potassium, but still more than our next set of nutrients, the micronutrients. These secondary macronutrients are immobile in plants. That means that plants cannot break down, recover, and transport these nutrients. One example of this is calcium, which is essential to the building of plant cell walls. If plants broke down their cell walls to recapture the calcium, they could not support themselves and would die. Since the nutrients are immobile, this leads to deficiency symptoms appearing in new growth first, which is typically at the top of the plant near its growing point or points. The last class of nutrients are the micronutrients. Plants need these nutrients in small quantities, but they do provide essential functions for healthy plant growth. Just to give you an idea of how little these nutrients plants need, a typical plant will need 1 million atoms of nitrogen for every atom of molybdenum. For chlorine, the ratio is higher at 333 atoms of nitrogen for every atom of chlorine. For comparison's sake, a plant will need 4 atoms of nitrogen for every atom of phosphorus. It is our job as gardeners to help plants get the nutrients they need in the correct ratios if we want to maximize growth, minimize financial costs, and protect the environment. Giving plants the nutrients they need in the right quantities and ratios is not a new idea. In fact, in the mid-1800s, Justus von Liebig came up with the idea of the law of the minimum. The law of the minimum is the idea that plant growth is limited by the scarcest resource or nutrient. To help illustrate his point, Liebig came up with the leaky barrel metaphor. Imagine that there is a barrel with different length slats. The slats themselves represent different factors like sunlight or water and all the different nutrients a plant needs. The height of those slats corresponds to the relative abundance of that factor or nutrient compared to the demand from the plant. The closer the factor or nutrient is to satisfying 100% of the plant's demand, the taller the slats will be. Plant growth is then measured by filling the barrel with water. As the plant starts growing, the barrel is filled with water. Eventually, the water will reach the lowest slat on the barrel and start spilling out. This represents the first limit to the growth of plants. The plant cannot grow anymore until that minimum factor is provided. Additionally, the plant will not grow more if non-limiting factors or elements are increased. An example of this would be if calcium is limiting plant growth, adding nitrogen will not help the plant grow further. We as gardeners must first address what is limiting growth before our plants can fulfill their full potential. Often the limiting nutrient for plant growth is nitrogen. This is because nitrogen is highly mobile in the ecosystem and plants need a lot of nitrogen compared to the other nutrients. Nitrogen is not tightly held on in the soil or by microbes and can move out from our gardens in multiple methods. Because of this mobility, we often have to apply nitrogen yearly. An example of this is the nitrogen we apply in the spring one year will not be in the garden the next spring. Nitrogen is used in high concentration in plants for amino acid and protein synthesis. In the soil, nitrogen is often found as ammonium, or NH4+, or nitrate, NO3. This diagram gives you an outline of the fate of nitrogen in our gardens. The nitrogen fertilizer we apply can be directly taken up by plants and soil microbes. The nitrogen can be lost from our gardens through bacteria turning some of that nitrogen into a gas. Nitrogen can also be leached out of the garden through precipitation or irrigation. As soil organic matter breaks down, it also becomes a source of nitrogen for our garden. For each percentage of organic matter you have in your garden, you will get about 25 to 30 pounds of nitrogen per acre. You want to be sure to account for this nitrogen when you're figuring out how much fertilizer to buy. Another important thing to remember is that when you apply compost to your garden, that nitrogen is released slowly. You can count on about half of the total nitrogen in your compost being released in the first year and 20% in years after that. You want to be careful of applying compost year after year and not accounting for that nitrogen being released from previous applications. Additionally, compost can have higher ratios of phosphorus and potassium compared to what our plants need. Since phosphorus and potassium are not as mobile as nitrogen, these nutrients can start accumulating in high concentrations in your garden. And this does not provide any benefit to you, your plants, or the surrounding environment. As a gardener, you want to be a smart manager of nutrients. In addition to providing nutrients themselves, you need to think about their availability to the plants. Fertilizer availability and when the fertilizers become available to the plant is dictated by soil microbes and the factors of the amount of fertilizer applied, the chemical or biological form of the fertilizer, soil water content, and soil temperature. Additionally, demand for nutrients from our plants is dynamic, with plants needing less nutrients when they are small and more when they are large. So the key is to try to match nutrient supply and availability with plant demand as much as possible. We will talk much more about this in later modules, but we want to make sure you're thinking about it now. Here are two helpful terms to remember. The two terms are immobilization and mineralization. Let's look at immobilization first. If you hear that a nutrient is immobilized, that means it is not plant available. Specifically, microbes have taken up that nutrient and incorporated it into their biomass. That nutrient must first become mineralized before the plant can take it up. Mineralization is the process of converting that nutrient from the gut of the microbe into something the plant can take up. Usually the nutrient must be converted from an organic form into a mineral form for the plant to take it up, hence the name mineralization. The other helpful term to remember is cation exchange capacity. Remember that cation exchange capacity, or CEC, is the amount of cations, which are positively charged, a soil can hold on to. This ability of a soil to hold on to cations is heavily influenced by both the clay and organic matter content. Cation exchange capacity is measured in milliequivalents per 100 grams of soil and can range between 3 to 100 milliequivalents per 100 grams of soil in different types of soil. So we have come to the end of the module on soil chemistry. Let's review what we learned. First off, soil pH is considered the master variable and has a big influence on the availability of different nutrients. We also learned about Liebig's law of the minimum and what a plant needs and doesn't need to help it grow. We learned about the differences between macro and micronutrients, and specifically about nitrogen and how that is often the limiting factor for plant growth. Thanks so much, and we'll see you in the next module.